Cool. Okay. Hopefully the missing went okay for you guys. Not sure how like the time works when you have to upload things from home. Okay. That's question 2. All right, let's start with question 1. So here you just have the same kind of question that we were doing in the last tutorial. So asking, are these allowed processes? So rather than drawing specific Feynman diagram vertices, they're just asking in general, is this process allowed? So for the first one, a Z boson to a B plus B bar. So this is fine. This is fine since, well, a pair particle production. So you can always think of the Z boson as kind of like a fancier version of the photon. So you can have a photon going through and make a pair production of a particle plus antiparticle pair. And Z bosons can do pretty much the same thing. So this is, you can imagine this is like a photon going to B plus B bar, but instead using a Z instead, in its place. For the second one, mu plus, so muon, anti-muon, I suppose, to an anti-tau plus a anti-mu neutrino plus a tau neutrino. So this looks to be fine. So on the right-hand side, the anti-tau and the tau neutrino, their lepton numbers are cancelled out. So your lepton number is conserved in this case. But the problem is that the tau mass, so the tau lepton's mass, is significantly larger than the muon lepton mass. So if you look at this process, you're going from something that's lighter to something that's heavier, plus additional particles. Even though neutrinos are very light, they're still going to take up some energy to produce them. And plus, they probably come out with some momentum as well. So by kinematics, you're kind of violating momentum conservation and energy conservation here. So this is kinematically forbidden. It's not violating any fundamental laws, but it's just not possible in terms of kinematics. Okay, and for C, an electron plus a positron plus a muon goes to a anti-muon plus an electron. So that's definitely no, because on the left-hand side, you have -1 electron lepton number and +1 mu lepton number. And on the right-hand side, this gone to +1 electron number and -1 muon number. So that's definitely not equal to each other. So violates lepton number conservation. Okay, for D, D is actually fine. Looks a bit weird, but if you just ignore the meson notation. Just think of it as a charm and anti-charm quark. Then this process goes like charm to anti-charm, and these two particle antiparticle kind of annihilate with each other and turns into a photon. And this photon then can pair produce electron positron. Yeah. So okay, fine with like asterisks, because remember we discussed this is like kinematically questionable, but in terms of like, is it allowed? Then yes. Okay, and for part E, you have a lambda baryon going to a kaon plus a neutrino. So in this case, it's a baryon number violation. So similar to lepton number, you look at baryon number. So you start off with 2 up quarks and a strange quark. You end up with an up quark and an anti-strange quark. So okay, the strangeness is also violated. But you should have, I always forget how much baryon number up quarks carry. Does it tell you in the beginning? No, it doesn't. I think it's a third. Yeah, I think it's a third. So up carries baryon number of a third. And strange is also a third. So on the gamma has total baryon number of +1. And the kaon plus has baryon number of 0 because there's an up and an anti-strange. So those two cancel out. And the neutrino definitely doesn't contribute any baryon number. Baryon number equals 0. So your left and right hand side baryon numbers don't match up. And also the strangeness doesn't match up. So definitely not allowed. So that's allowed, that's not allowed, that's not allowed. That's allowed, that's not allowed. Any questions on that? I've got a lot in the chat. Would DEED also fork with a Z boson? Yeah, that's right. So it worked with a Z boson as well. For 1E, doesn't US correspond to a sigma plus and not a lambda particle? Very possible. I actually don't remember the A4 path that well. Let me check. Lambda baryon. Yeah, you're right. Lambda is a UDS. So what is a US? Sigma is UDS as well. What? Sigma plus. It's like the baryon number conservation. It definitely doesn't work, but I'm just curious now. What's this? UUS, it is sigma plus. Yeah, you're right. Yeah, so technically this is a sigma plus. Okay. Cool. Let me get rid of some of these. Okay, so for 2, super KEKB is an electron-positron collider, which collides an electron at 7 GeV with positron 4 GeV head on. So yeah, the momentum's opposite directions. Neglect the electron-positron mass because they're ultra relativistic. So it's a fair assumption. For part A, calculate the center of mass energy. So hint, use Mendelssohn variable. So yeah, let's use that. So S is equal to P1 plus P2 squared by definition. So I'm just going to call 1 the electron and 2 the positron. And that would equal E1 plus E2 all squared minus P1 plus P2 squared. And okay, since they're coming at head on, so P2 momentum is like, sorry, P2's direction is like P1's opposite direction. So they're coming, so I can replace this with a minus sign. So, sorry, direction. So E1 plus E2 squared minus P1 magnitude minus P2 magnitude squared. So that's just telling you that they're facing in opposite directions. Okay, and now I can make this approximation that since they're ultra relativistic, so then the energy is square root of P squared plus M squared. And if mass is almost like negligible in this case, then E is just approximately P. So this I can write as E1 plus E2 squared minus E1 minus E2 squared. Just making the ultra relativistic assumption here. Okay, and now I can say that this is perfectly calculable now because we have the energy. So E1 is 7 GeV and E2 is 4 GeV. And I can just plug it in. So energy at the center of mass is equal to square root of S. So that's square root of 3 plus, wait, not 3. 7 plus 4 squared minus 7 minus 4 squared. So that equals 11 G, not 11, 10.6 GeV. And that's the center of mass energy. Okay, B, and then calculate what is the heaviest particle you can produce in pairs. So the easiest way to do this is just to go into center of mass frame. And produce them at rest. Because if you're at the center of mass frame, that means you're at a frame where, from your perspective, the electron and the positron comes in and they will exactly collide in the middle. And this collision point will be at rest from your center of mass perspective. And so from this point onwards, all the energy is stored at this point and used to produce particles. If you produce them with some momentum, to conserve momentum, they have to go off in like bipolar directions to cancel each other out, cancel each other's momentum off. So that's just wasting energy on giving them momentum when they're just canceling each other out. So the best way to give all of the energy to the mass is to go to the limit that these two momentum goes to zero. So producing them at rest. So you end up colliding them and you just got two particles sitting here, or particle, antiparticle sitting here. So producing them at rest, and since they're the same particle, which is particle antiparticle pair, so they should have the same mass, then the mass of each particle is just the amount of energy that's available to produce them divided by 2, because you're going to make 2 of them. So 5.3 GeV. Cool. Any questions? No, all good. Okay. Then for question 3, consider Lagrangian of 2 scalar fields phi and chi, and you get the Lagrangian of phi, Lagrangian of chi, and then an interaction Lagrangian. And each of them take this form. So you got your kinetic term and your mass term, and then a 4-point vertex, and also the interaction vertices. So determine the possible complex numbers omega for which the Lagrangian L is invariant under the global symmetry transformations. So these two. So if I make these two transformations and I don't know what omega is, what does omega have to be to keep these Lagrangians invariant? Okay, so so looking at some of these terms, so you got these phi star phi terms, and since these are global transformations, then you know the d phi star d phi term, they will just transform the same way as phi star phi. So I only have to look at phi star phi to convince myself that this transformation is going to be invariant, then it should be fine. So in this case, phi star phi will equal phi, not equal, sorry. So if I transform them, then it will become phi star omega phi. So if that has to be invariant, that's magnitude omega squared phi star phi. So that tells me if omega is a complex number, then the magnitude of it has to be equal to 1. And then, yeah, so that's the phi star term. And the other one is the chi squared term. So this one has to also be invariant. So if I transform chi squared, then it becomes omega squared chi all squared. And that just becomes omega to the 4 chi squared. So that also tells me that omega to the 4 has to equal to 1. So that's just the 4th root unity of a complex number. So that means omega can equal plus or minus the imaginary unit, I. And that satisfies this condition. So the magnitude of it is 1. And if you take the 4th power of it, it's going to be 1, regardless of whether it's plus or minus I. And now you just have to now demonstrate that for these interaction vertices, this omega also works. So it's not ruining anything in the interaction terms. So the first one let's look at is the phi star phi chi squared. So that just equals, not equal, sorry, I keep writing equal, transforms into phi star omega phi omega to the 4 phi, not phi, chi squared. And by definition, this just equals phi star phi chi squared. So that's fine. And then phi squared chi transforms to omega squared. Doesn't W equal plus or minus 1? also works. It does. It might. I think because then this will be trivial, and this will be almost trivial. So maybe it's like not considering the solutions because it's not transforming anything in that case. But you're right. Yeah, it technically works. So like for fourth order root of unity, then like plus or minus 1 also works. Yeah. But it kind of makes it a bit boring because then chi doesn't transform at all. I guess I should okay, minus 1 will be non-trivial for phi, but will be trivial for chi. Yep. Okay. So phi squared and then omega squared chi. And that equals omega to the 4 phi squared chi. So that is obviously fine as well. And then the last one, phi star squared chi goes to omega star squared phi squared, phi star squared, omega squared chi. And yeah, this one it still works because whatever phi is, whatever omega is, whether it's plus or minus I or plus or minus 1, this will equal minus 1, and this one will equal minus 1. So the two of them will just cancel out. And yeah, so all of them are fine. So any of the roots will work. All right, cool. Any other questions? Okay, if not, then let's look at the scattering question. Okay, so consider a scalar particle chi with mass m chi and a scalar particle phi with mass m phi, together with its antiparticle phi bar. Relevant Feynman rules for propagators and vertices which contribute to the matrix element I M are these two propagators and these two vertices. I'm not gonna lie, this kind of confused me because like these arrows generally refer to some kind of conserved quantity that you want them to be continuous, but since it's scalar particles in this case, it doesn't really matter, but it's just, yeah, it might look a bit weird, but the arrows in this case is purely to designate whether it's a particle or antiparticle. So if they're going left to right, like forward in time, there's a particle. If they're going right to left, then is an antiparticle. But yeah, you don't have to worry about like fermion lines or anything like that, where it has to be kind of flows through. They can end up at a dead end and not ruin anything. Okay, now draw the leading order Feynman diagrams which contribute to this process. Oh, pen. This process. Okay, so you actually have all three channels. So S channel gives you so two particles going forward. Let's call this P1, P2, phi propagator, what's it called? A chi propagator. And then two going back in to show that these are antiparticles. So that's P3, P4. And you got two vertices. And then you can also have the T channel. So, whoop, already drew it the wrong way. Like that. So again, two particles going in, P1, P2, and then P3, P4. And because the end state particles are identical, so that means we do have to worry about a U channel where we can swap the end particles because there's no way to distinguish them. So you don't know which vertex they came from. So you can have one P1 coming in, P2, P4, P3. Oops, I drew this one wrong again. Arrow going in, and that's a 3. So that's your STU channels. Okay. Show that the matrix element is given by this thing. Okay, so the first two terms should be fairly obvious. The only thing is the last term. So for all of these, this one, the propagator would just be I over P1 plus P2 squared minus m chi squared. So that's just S. So it's I over S minus m chi squared. So similarly, this one, I over P1 minus P3 squared minus m chi squared. Then that's I T minus m chi squared. Whereas this one you have I is P1 minus P4 squared minus m chi squared. So then there's I U minus m chi squared. And then each one of them then contributes a vertex of minus I kappa. There's no external line, so you don't have to worry about that. So you just pick up a minus I kappa here, minus I kappa here. Same for here. So then each one of them just gets a minus I kappa squared. And the total amplitude is just all of these added together. Okay, I take an I out of front as well. So 1 over S minus m chi squared plus 1 over T minus m chi squared. Okay, and instead of the U minus m chi squared, I'll use that relation that we derived in one of the tutorials. S plus T plus U is equal to 4 times the mass of the particle, m5 squared. So then U is equal to 4 m5 squared minus S minus T. So then this is 1 over 4 m5 squared minus m chi squared minus S minus T. Oh, I took a factor of m. Oh, this one. That's just how it's defined. So minus im is the, or is it just im? Sorry, it's just im. There's no minus. Im is defined as like the probability of this one diagram. And then the amplitude of this one diagram. So then im is technically the vertex, the propagator, and then the other vertex. Does that make sense? Yeah, it's just the definition. Yeah, if you write down, if you sum up all the terms inside the diagram, it's technically equal to I times the m. Okay, and then just clean this up. The minus I squared just becomes a minus 1. This I cancels out with this I. So then m equals minus kappa squared, and then all the terms in the bracket. Said, okay, for completeness, this is the S channel, T channel, U channel. And this is the total. Okay. Is everything else cool with everyone for this? All right, all good then. Okay, and now we want to derive a mathematical expression for the Lorentz invariant differential cross-section d sigma dt. Okay, so in the formula sheet, I think you're given one of them. Okay, you're given like this, which can tell you d sigma d cos theta. So then you just have to transform this to d sigma dt. So we'll be taking this as given. So down here we'll say that, okay, d sigma d cos theta is lambda half s, and then this is like M3, M4, is it, I think? Yeah, M3, M4, so the two final state masses. And the one in the denominator, the F, is the two initial state masses. But since we have phi to phi bar, all their masses are M5. So that means M1, M2, M3, M4, they're all equal to M5. So I don't really have to distinguish between the two. So this is just M5 squared, M5 squared. Divide by 64 pi s. And then there's another, so that's from the F, the flux factor was S lambda half. M5 squared, M5 squared, and the magnitude squared. Okay, and since, yeah, I said the two Callan functions, because of the symmetry between the big start and end state, then these two are the same thing, so I can cancel them out. So this just simplifies a lot into 1/64 pi s m squared. Okay, and before we get excited and plug the m into this, we need to first turn this into d sigma dt first. So to do that, same as the tutorial, so P1 minus P3 for the t minus sign variable, 2m5 squared, since P1 is the phi, P3 is phi bar, but they both have m phi. So P1 squared and P3 squared all equals m phi squared, minus 2 P1 mu, P3 mu inner product. So that's just 2 E1 E3 plus 2 P1 P3 cos theta. Okay, and now we just do dt, d cos theta is equal to 2 P1 P3. And remember, these guys can be related back to the Callan function, so it equals lambda s m phi squared over 2s. So yeah, remember that P1 or 3 can be equal to lambda half over 2 root s. And P3 also equals that. So two of them together just cancel out the 2, gives you one of these and s on the bottom. Okay, then d sigma dt will be d sigma d cos theta dt. So that's 1/64 pi s m squared 2s on lambda. S's cancel out, and the 2 cancels out with something, but that's about it. So 1/32 pi lambda m squared. Okay, now we can put in this m. Welcome to the symmetry factor. Oh yeah, sorry. I skipped a step here. So I expanded up bottom where f and also sf. So sf is equal to half. F is like 2 lambda half. So sf a half. So these two, this 2.5 canceled out. So we're left with only just that. Because the symmetry factor for this, you have oh, sorry, maybe the other way around. What's f again? Flux factor. Yeah, sorry. Okay, so f is lambda half on 2, and then sf is equal to 2. Sorry. So then this half cancels out with this 2. So yeah, in the denominator, you just f times sf, which is equal lambda half. Yeah, sorry, I skipped a step. I just write out here for completion. So f times sf is equal to half lambda to the half 2 factorial. So this equals lambda to the half. There we go. Okay, and now I just plug in this m into here. So that gives me a kappa to the 4 from the out the front with my 32 pi lambda. S m phi squared, m phi squared. And now I get everything else in the bracket squared. Okay, so I want to get everything in terms of S and T. Looking pretty good so far. So the only thing left is this Callan function. I can't actually just evaluate this because Callan function of x, y, z is x squared plus y squared plus z squared minus 2xy minus 2yz minus 2xz. So then lambda of S m phi squared is S squared plus 2 m phi to the 4. So y squared and z squared both are the same. Minus 2s m phi squared minus 2s m phi squared minus 2 m phi to the 4. I might have got one of these other way around, but yeah, that's the total amount of terms you should be getting. So this 2 m phi to the 4 and this 2 m phi to the 4 cancel each other out. So I end up with just s minus 4 m phi squared. And I can put that back in there. So now I have my d sigma dt that's in terms of only s and t, and these mass parameters and the coupling, I can't do anything about them. So that's fine to leave them alone. And that's the solution for that one. Just write that in full. D sigma dt